Hello for all, my name is Yuri from Brazilian Navy and I'm here to present to you the paper Parameter Dependent Surface to Air Missile Autopilot Design that I elaborated with Jacques Waldman from Instituto Tecnológico de Aeronáutica. These are the topics of the presentation. I will first introduce the problem and the motivation of the work. Then I will describe the main goals, missile LPV model, and the loop shaping proposed method. At the end, I will explain the controller design and the results of the nonlinear interception simulation. Missile Autopilot has to ensure high performance and robustness over a large range of operational conditions that affect missile dynamics. Although classic game scheduling designs have been successful in practice, they do not provide theoretically guaranteed characteristics. We propose to describe missile plant as a polytopic LPV system and use loop shaping infinite control technique to synthesize an autopilot that ensures performance and robustness for all operational conditions and in presence of plant model uncertainties, control action minimization, and noise attenuation. We also propose make loop shaping weights also parameter dependent, that is our mainly proposed method. In order to obtain a polytopic LPV descriptions of the missile, we developed a longitudinal model as a function of angle of attack alpha. The lateral model is similar. For design purposes, we establish a sea level scenario at Mach 3 and missile speed constant. So the model is numerically defined here and has two states, angle of attack and pitch rate, pitch actuator deflection as input, and missile acceleration in body Zx as output. Note that the model has two time varying parameters, m alpha and m delta, that are nonlinear functions of alpha, which we assume that can be measured. Polytopic LPV systems are those that state space matrices depend on time varying parameter vector theta of t that varies inside a polytope with vertices xi. Then we define theta as m delta and m alpha for our missile longitudinal LPV model. Vertices xi are composed by minimum and maximum values of m delta and m alpha. State space matrices also varies inside a convex polytope whose vertices are a function of xi here, and state space matrices are also parameter dependent in a convex composition of their polytope vertices here. Figure shows classic 4-block loop shaping age infinity control approach. G is the plant model that we call nominal plant. W1 and W2 are the weights to shape singular values of the nominal plant and achieve the desired performance. Key is the stabilizing controller obtained via H infinity norm minimization. The final controller is obtained by composition of the stabilizing controller K and weights. When applying loop shaping for polytopic LPV systems, we have some limitations that are usually only matrix A of shaped plant is described as parameter dependent, and the weights must be the same for all vertices. We proposed obtain a parameter dependent output H infinity controller by means two loop shaping configurations with 8 weights partially parameter dependent and totally parameter dependent. The use of one or another will depend on the design requirements of the problem. In both cases, the plant must be described as a polytopic LPV system and must have matrix D equals 0 and matrix A as parameter dependent. When partially parameter dependent, the weights have only two matrices as parameter dependent, here and here. Using block connection, we can calculate the shaped plant G of S that has the same form of D, only matrix A as parameter dependent, and all standard theory apply. However, when totally parameter dependent, the weights have all four matrices as parameter dependent, here, here. Besides that, shaped plant has three matrices in this form, here. Then we need to change the standard approach to solve the synthesis condition. Our proposed solution is to make the stabilizing controller in the form only matrix A as parameter dependent and matrix D equals 0. So we obtain a new synthesis condition based on LMI, and the final controller is clearly described in a gain schedule parameter dependent polytopic form. We use the first proposed configuration for Autopilot design. We define weight 1 as a first order low pass filter, and this is one state space realization. Parameter to be set is eta I, and we achieve the requirements with eta equals 300 for all vertices. We define weight 2 in the form of pi filter, where this is one state space realization, and parameters to be set is zeta I and micro. Note that the micro does not change at the vertices because we use first proposed configuration. We achieve the requirements with micro equals 0.001 for all vertices, and zeta was selected as 0.05 for vertices 1 and 3 and 0.01 for vertices 2 and 4. These are the singular values of all four vertices of the non-shaped plant in blue and for shaped plant in red. Note that the behavior of the shaped plant is identical for all vertices at low frequencies, less than 10, and at high frequencies, above than 200. Such result could only be achieved by using the proposed loop shaping with parameter-dependent weights. We also performed a controller order reduction, eliminating the three fastest poles. The new K reduced has order 5 and also achieved the requirements defined. The order reduced Autopilot was tested with a 6 degree of freedom nonlinear simulation implemented in MATLAB. We emulate engagements against a subsonic aircraft trying to evade with a 3G random maneuver. Two scenarios were considered. Scenario 1, target approach the missile head-on. Initial target position and velocity are defined here. For both scenarios, the initial target position in X is a random value between 2 and 4 kilometers, emulating a secret detection. We performed 100 realization and we obtained average miss distance of 3.2 meters, standard deviation of 2.69 meters, and successful impact rate of 98%. That is for a considered warhead lethal range of 10 meters. Here. Scenario 2, target initial attempt to outrun the missile in a tail chase. This is the difference in the initial condition. The results were similar to the first scenario with a successful impact rate of 97%. That's all, and this is my email for necessary future contacts. Thank you.